Thank you to all the speakers for a great presentation. Maybe Dung, you can stop your sharing, then people can see me. Okay, good. That's okay. So we do have a very variety of presentations. We cover a wide range of areas, from nanomaterials, functional materials, to fibers materials, to passive sorption materials, and hemp concrete, hemp materials. And we basically covered a larger scale, right, from nanoscale to the building scale, and what's the implication of these materials on the indoor air quality. And that's exactly what the Annex 86 subtask 3 is focused on. So we have a few questions for all the speakers here. And I'll start with the questions for our first speaker, Professor Menghao Qin. The first question is about the materials. So is it possible to combine the MOF materials with other active materials such as catalyst?
Yeah, yes, it's very much possible, because Morph is also a kind of catalyst. Yeah, you can change the size of the linker to be smaller and to be large, and also combine some functional material inside the cage of Morph. So that it's very much possible.
Good, thank you. And second question is, how would this material perform in the real environment? For example, how the temperature and the humidities impact the material's performance over the usage time?
Yes, that's a very good question. Maria, I'd like to share my screen. So could you please enable the function for share for me? Yes, thank you. Yes, I share one screen, because this is measured Morph performance in real built environment. It's one of our main research target. You see on the left, on the right-hand side, this is isothermal under different temperatures, 20 degrees C, 30 degree, and 50 degree. So this is the moisture water vapor isothermal. So you see, with the temperature increase, the isothermal is significantly changed. If the temperature is higher than 50 degrees C, which means this material will release all the moisture back to the environment. So this is the regeneration temperature. But at our normal temperature, room temperature, 25 degrees C, it's a very S-shaped, very good S-shaped isothermal. So this is one of the main feature of Morphs, because they have relatively low regeneration temperature. This, if it's zeolites, this number should be around 150 or even higher. So
thank you. We have a few more questions coming back to you, but I will reserve that for later if we have time.
Okay. Yeah.
I want to go to the other speakers.
Yes.
Yeah. Thanks, Menghao. I have a question for our second speaker, Dr. Doyun and Mitra, Bahri. Okay. The first question is about the CFD model and using CONSOM 2. Whether you use the steady state or transient simulations.
The first step we started to work on is the steady state. And then we are looking to go for the transition states.
Great, thank you. Okay. And second question is, it's based on your simulation, right? Your CFD simulation for the research house. Does your simulation results show whether the controlling factor for the absorption of the VOCs, is it limited by the materials, or it is limited by the convective mass transfer across the boundary layer over the surface of material?
That's something that we were facing too. Yeah, it's a kind of the concentration around the boundary layer, one of the limitation factor that we have. So it's the reason that for a high concentration, the behavior would change. So we are still, as I mentioned, it's kind of the beginning of the modeling that we have started, and it's a lot to do with that. So yeah, I can say that the boundary layer concentration is a very important factor for us here.
Yeah, I think it's a very interesting study. Certainly the flow rate depends on the ventilation rate in the space, the air distributions, and the location of absorption materials.
Exactly, yeah.
Another quick question is more for clarification. Is that you mentioned about the painted gypsum wallboard versus unpainted gypsum wallboard, right, for absorption. And when the paint was added on, the absorption capacity reduced significantly. Have you tried different paint? Some paints are more porous compared to others.
It's Bob and Jeremy's experiment. So I don't have a lot of information, but I think they tried several of them. So they tried to find the most porous one. So that's the result we used.
I see. Okay, that's very interesting, very useful study, because in the real application, people will put paint on the wall.
Yeah, exactly. Yeah.
Very nice.
May I add something else? They have also used the breathable paints with different kind of depth to see what would be the effect of the, when we increase the length, the weight of this paint or reduce it. And there is one report, internal report that we have in NRC. I think because it was from the manufacturer, I'm not sure if we can kind of publish it or not, but they have worked on that kind of very extensively too.
Mm-hmm. Yeah, that's certainly another area for research.
Yeah.
Mm-hmm. Thank you very much. I move to our third speaker, Professor Alireza Afshari, and some questions for you. The materials the spinning fiber and the composite filter you're developing, I think it's quite interesting. Okay. Now, if you scale up your composite filter to a real house, or whether it's a Danish house or American house, what would be the equivalent ventilation rate that filter can provide?
You are asking for the ventilation rate when we have installed the filter. That is what you mean?
No, my question is, like I say, in a typical house, we say we have like a 0.25 to 0.5 air changes per hour, right? Yeah. Typically, right? If you use your filter for a house like that, how much more equivalent ventilation rate that filter can provide?
We didn't test it actually, and we didn't calculate it. That's a very good question for the PhD that focus on that and make a calculation. I like your question, but I don't have answer directly to give you.
This is, yes, thank you. It's more of a practical question there.
Yes,
People
exactly.
always asking about, okay, how does air cleaning compare to ventilation? So at least I think we can produce materials or technologies that can compete with ventilation.
Actually, if you look at also this material is not only used for natural ventilation, we can also use it for, air cleaning, portable air cleaning in the building. So it's very relevant, and but still we have the same problem that how much chemical substances we can remove from the air. That's still a very big question regarding our material also. It is not 100%. It is with toluene only around 30 to 40%. So still we have problem with 60% that we cannot remove.
Sure. Yeah. Thank you very much. Yeah. Another quick question is just for clarification. I think one of the tests you use the charging. You charge the particles in the airstream, and then let the filter to collect it, which will certainly increase the efficiency, removal efficiency. what kind of voltage do you use to charge the air? And does it produce any ozone, that particular technology?
I think we have always, when you use actually a kilovolt less than say 7 kilovolt, so it is very low level of the ozone. When you come in close to the 1000, so you generate a lot of ozone. So actually my understanding is that you have ozone, but you cannot measure it actually. You have very low level of ozone, so you cannot measure it. But you can say we didn't have ozone, we didn't find ozone, but I don't believe that. I think we had ozone, but we cannot measure it.
Yeah, okay. Thank you. Yeah, again, that's a very interesting study. I'm looking forward to the new further results coming out from your research. Let me see. Okay. Yeah, I will move to our next question, to next speakers. Again, it's a very interesting study, Professor Tran, that this coupled heat, air, moisture, and pollutant simulation is actually very challenging, right? So the question here is, there's always interactions between VOCs and the water vapor. Right, when both VOCs and water vapor are dissolved on the materials, how would you model that? And this is more of maybe an open question. I don't know whether you have already considered that or you are still working on this.
Yeah, thank you, Jensen, for the question. It's a very interesting question now, because many studies show that the impact of humidity and temperature on VOC emission is very important to study. However, for the numerical model developed, if the data are available, we can do the simulation. However, today, up to date, there is no theoretical correlation between the VOC diffusion coefficient and also VOC partition coefficient and humidity. Therefore, I think we need to realize the experimental work, and we can also propose the empirical formula to relate the impact of humidity on VOC behavior of building materials. However, if necessary, we can also use a simulation in order to predict the behavior of VOC. So from the behavior of VOC behavior of building material, we can propose some for example, some formula in order to establish the relationship between VOC coefficient, for example, partition coefficient or diffusion coefficient, are function of humidity. And of course, that is very complicated because that depends also the pore structure, that depends also the microstructure of the pore, dimension of the pore, and should be very complicated. And also competition between water vapor and VOC should be very interesting to study. However, we need to do many experimental work to respond this question. Yeah.
Yes, I very much agree. Thank you. Yeah.
Thank you, Jensen.
Also, I think this certainly is an interaction between VOC, water vapor, and materials, the three things, and the environment. We also have temperature and humidities.
Yeah.
The VOCs has also many different type of VOCs. We have polar versus non-polar.
Yeah.
Some VOCs can be absorbed by water, and others are cannot be absorbed. Like formaldehyde versus toluene, they have very different behavior.
Yeah.
I think the same question, basically the competition between VOCs and the water vapor absorption, okay, by materials. The same question applies to the morph materials, right? The morph materials. I think there's a question here coming back to Professor Menghao Chen is
Yeah, very interesting.
Morph materials. If the Morph materials deal with both VOCs and water vapor, it has a very strong absorption for moisture.
Yeah.
When you have these both together, how would you design the Morph materials? You know, what properties you can actually tweak on the Morph materials so that it can absorb both VOC and water vapor?
Yeah, that's a very good question because we just finished the experimental test last week, and then we tested the new Morph, and then maintain the same the formaldehyde absorption capacity on the different humidity levels. And then the main if you go to the microstructures, it's not a pure physical absorption, it's a hemisorption. So we add some other functional group to the ligands, for example, the perazone-based Morph. So there is a little weak chemical reactions during the formaldehyde absorption.
Yes.
So that will, yeah. So the formaldehyde with water and together with the Morph, and then we generate primary alcohol. And then this alcohol, it can be and regenerate this Morph is also relatively simple. You just put in the water for 2 hours, and then all the formaldehyde will disappear, and then dry it. You can use it again. So it's with low energy consumption or regeneration.
Yeah, I think I very much agree that I think this material has great potential, and at the same time, there's also a lot of challenge, I think, to push it to the real applications.
Yeah,
you mentioned about if there's a chemisorption, I think because it's a catalyst, essentially it's a catalyst. So there's some catalytic reactions and which can produce some byproducts too. So what kind of byproducts are they important?
yes, the next step we'll do the PTMR test to analysis is there any byproducts for this particular Morph. But I want to mention for moisture absorption, this is pure physical absorption. There is no byproducts. It's very simple, very clear. It's pure physical absorption. But for VOCs, there will be some chemical chemisorptions. So that's a different mechanism.
Yeah. In terms of on the application side, the materials you used or you produced, how costly it is? If I see you coded to the coil, the evaporators and condenser coil.
Yeah.
At that scale, on the cost side, is that practical these days?
Yes, it depends on which type of Morph. There are many types of Morph. Some Morphs are very expensive. They are the ligands are very expensive. The metals also very expensive. But we developed with our colleagues, and then there's some green bio-based Morphs. So the raw materials is from sweet corn, so it's very cheap. And then our prediction is that for large scale production in the near future, the cost of those bio-based Morph will be the same magnitude as zeolites.
Yeah,
so it will be acceptable, practical for industry application.
Yes. Okay. Let me see any other questions from audience. I think we're also short of time here.
Yeah.
Maria, how much time do we have?
Well, we are past.
We're past
our
okay. Yeah.
agenda.
So yeah, I think we addressed most of questions, and if you have any other questions, please complete it in the Q&A, the chat space, and we can respond later, and we'll try to get the speakers to respond to your questions. At this time, I'd like to thank you all for your participation, and I also thank for the organizer, Maria. She spent a lot of time with us organizing this session. I really appreciate that. And thanks to all the speakers again. Thank you.